So what does it really take to create a perfect angle in a piece of metal? You might think, hey, that's simple, right? But in the world of precision engineering, getting even a single bend just right is, well, it's a huge challenge. Today, we're going to dive into the hidden science behind this whole process, and we'll meet the one stubborn force of nature that's always trying to undo all that hard work.
I mean, have you ever tried to bend something simple like a paper clip, only to have it bounce back just a little bit the second you let go? Yeah, that tiny, almost unnoticeable movement is actually one of the biggest headaches in all of modern manufacturing.
Well, this bouncing back thing actually has a name. It's called springback. It's just the material's natural tendency to want to go back to its original shape. And for engineers who need parts to be perfect, I'm talking down to the micron. For everything from a car door to a satellite, springback is the constant enemy they have to outsmart.
So how do they do it? How do they beat springback? Well, it all starts way before any metal ever feels the force of a machine. This is stage one, the blueprint. This is where the battle is basically won on paper, with pure calculation.
Okay, so before you can even think about doing any math, you have to understand the material itself. I mean, really understand it. Engineers look at its properties, like elastic modulus, which is just a fancy way of saying how stiff it is, and its yield strength, which is the exact point where it bends and decides to stay bent. But you know, the most critical factor, the one thing that can literally make or break the entire process, is something called the rolling direction.
So why is this rolling direction so incredibly critical? The best way to think about it is like the grain in a piece of wood. If you try to bend the metal against its invisible grain, chances are it's going to crack and fail. But if you bend with that grain, you get a perfect, clean, strong bend. It's a tiny detail that makes the difference between success and total failure.
All right, once all those material properties are locked in, the real challenge begins. See, you can't just fight springback head-on. You have to be smarter than that. You have to work with it. The whole key is to predict exactly how much that material is going to want to bounce back, and then you use that prediction against it.
So for this project we're looking at, the goal is all about precision. The engineers need to create a final, finished bend of exactly 105 degrees in a sheet of aluminum. Not 104, not 106, 105.
After running all the numbers on the aluminum's stiffness and strength, the engineers make their prediction. They figure the material is going to spring back by half a degree. Now that means, as soon as the bending force is removed, the angle is going to open up by 0.5 degrees, which would totally ruin the part, unless, of course, they've planned for it.
And that brings us to the big question, right? So how in the world do you get a 105-degree angle if you know for a fact it's going to spring back half a degree on you?
This is where the magic happens. You have to outsmart the material. You compensate by overbending it. The tool, or the punch that actually presses the metal, it's not set to 105 degrees. Nope. It's machined to a sharper angle, 104.5 degrees. The whole plan is to bend it just a little too far, so when it springs back that half a degree, boom, it lands perfectly at 105.
Okay, so that's the theory. Sounds good on paper, right? But does it actually work in the real world? Well, in stage 2, we move from the blueprint into the lab to put these calculations to the ultimate test.
So here we are, in the lab. You can see the aluminum sheet is placed in what's called a V-die. It's sitting right under this massive machine called a press brake, and that special 104.5-degree punch is about to come down and form the bend in just a matter of seconds. The press comes down, the bend is made, and yeah, to the naked eye it looks pretty darn perfect. But in precision engineering, looks good just doesn't cut it. It's meaningless. They need hard data.
And to get that data, they turn to digital analysis. They take a super high-resolution photo of the bent part and load it into this software that can measure the final inner angle down to 1,000th of a degree. This is it. This is the moment of truth. Were all those calculations on the blueprint actually correct?
And here we go, the results are in. The target was a perfect 105 degrees. The final measured angle, 105.473 degrees. I mean, that is astonishingly close. It's a real testament to just how accurate those initial calculations were.
Just to put that into perspective for you, the deviation from the target was only 0.45%. That's tiny. In the world of manufacturing, where parts in a jet engine or a car's safety cage have to fit together flawlessly, this isn't just a success. It's proof that the theoretical model works, and it works beautifully.
But wait, we're not done yet. Modern engineering doesn't stop there.
There's one final step to make sure this whole process is repeatable and reliable, all without wasting a bunch of physical material. Welcome to Stage 3, the digital twin, where the entire operation gets replicated inside a computer.
So using some seriously powerful simulation software, engineers basically build a virtual factory. They start by importing the exact 3D models of the punch and the die. Then they plug in the exact same material properties we talked about earlier, stiffness, yield strength, and of course that all-important rolling direction. They program the virtual press, and then, most importantly, they check the box to enable the springback calculation.
The computer then just goes to work, crunching all the numbers, simulating all the complex forces and stresses on the material. And what you're seeing right here is its prediction, the final shape and angle of the part after that simulated punch is removed and the metal does its little springback dance.
And the final number that the simulation spits out? 105.617 degrees. Again, that is remarkably close to both the blueprint's target and the actual real-world experiment.
Okay, this is it. The moment we've been waiting for. We have our number from the theoretical blueprint, we have our measurement from the real-world lab, and we have our prediction from the digital world. It is time for the final verdict.
Just look at this. Look at how incredibly consistent these numbers are. The theoretical target was a perfect 105. The physical experiment gave us 105.473, and the digital simulation predicted 105.617. All three of these completely independent methods gave us results within just over half a degree of each other. That right there is a powerful validation of the entire engineering process.
The engineers who ran this whole project, they summed it up perfectly in their final report. They said that the strong consistency between all the results proves their process is sound. In other words, the system works. Theory, practice, and simulation, they're all telling the same.
So what does it really take to create a perfect angle in a piece of metal? You might think, hey, that's simple, right? But in the world of precision engineering, getting even a single bend just right is, well, it's a huge challenge. Today, we're going to dive into the hidden science behind this whole process, and we'll meet the one stubborn force of nature that's always trying to undo all that hard work.